We are recording, and we're really not picking up any new material compared to what we spoke of on Wednesday. We're still looking at what happens when we add heat to a material. And the two answers, I think, are it either increases in temperature or it changes phase. On the other hand, if we remove heat from a material, it either decreases temperature or, again, a possibility is it changes phase. And I think that phase change part, and by that I mean going from a solid to a liquid, maybe from a liquid to a gas, that thing, that aspect of what happens to materials sometimes had a little bit of confusion associated with it. And so I've got a graph that I had in last night's video that I want to show you just to make sure everybody's got the idea. So let me share my PowerPoint with you. And of course, after I go over just a couple slides, we'll do some questions, and then I got some problems for everybody to do. All right, so phase changes. This could be water, this could be mercury, this could be nitrogen. I guess it has a solid and a liquid and a gas form. We're used to it in the gas form at our room temperature, but every material goes through this process. And if you start all the way over on the left, you've got a solid material. And you can see it's starting in this case for water at about, I don't know, minus 60 degrees Celsius. Heat is added and the temperature goes up. The ice doesn't melt. The temperature goes up. The ice doesn't start to melt until that horizontal section right there along what's labeled as number 2. Okay. At 0 degrees C, water goes from its solid phase, ice, to its liquid phase, and it stays at 0 degrees C until all of the material has melted. And the assumption here is, of course, everything's at equilibrium, that it's perfectly mixed, and that everything is in thermodynamic contact with everything else and comes to equilibrium. And so 100% of the solid changes to 100% of the liquid at 0 degrees for water. Okay, once everything is liquid, then heat is continued to be added here. And you can see the x-axis is time, right? This is happening over time. And so along curve 3 here, what we're doing is we're adding heat to cause the temperature to increase. And eventually we get the temperature of the water to 100 degrees. And when all of the water is at 100 degrees Celsius, the water starts to boil and the liquid phase goes into the gas phase, steam. And that happens along curve 4 right there. And until all the water is converted into steam, the steam also in contact, in thermal equilibrium with the water, stays at 100 degrees C. Now, obviously, if it's free to go throughout your kitchen because it's coming out of a steam kettle or something, it's no longer in equilibrium. But if you keep it, the boiling water that's turning into steam in a container where there is equilibrium between the steam and the water, it'll stay at 100 degrees. And if you continue to put heat into it, of course, the steam warms up and can go to whatever temperature it wants to, I guess, until it becomes a plasma, but we don't talk about that. There is one other possibility you may have heard of, particularly the chemists maybe. It is possible to go from the solid state to the gaseous phase. You have to put in an awful lot of heat very quickly to do that. I believe that's called sublimation. We don't talk about that in this course, but it is possible to go from line 2 right there at 0 degrees C all the way up to 5 and create steam off of ice. Okay, but we're going to ignore that possibility. I don't have numbers to tell you how much heat you have to add to cause that to happen. We'll stay with the things we've talked about. All right, two equations then that we spoke of on Wednesday, which haven't changed. We're just going to be reviewing them here. The problem today will get a little harder. I guess we'll have 3 objects instead of just 2 things or 1 thing. The amount of heat we add will cause a temperature change, and they're proportional, but it also, there's a factor of mass and this property of a material called the specific heat. Okay, so the specific heat talks about the heat that raises 1 kilogram of some substance by 1 degree Kelvin. And we said last time, hopefully you remember, 1 degree Kelvin in temperature change is exactly the same as 1 degree Celsius. Of course, it's not at all 1 degree Fahrenheit or the absolute scale associated with Fahrenheit, the Rankine scale. 1 degree of Kelvin is only equal to 1 degree change in Celsius. In any event, Q is equal to MC delta T. That's good as long as there is no phase change for water, as long as you're not at 0 degrees or at 100 degrees. Here's some typical specific heats of solid. You'll see in the worksheet today, I had to add glass. The specific heat of glass is 840, and the units are joules per kilogram per Kelvin. And of course, that melds neatly with this equation, because if C is in joules per kilogram per Kelvin, it could be joules per kilogram per Celsius, since 1 degree change of Kelvin is equal to 1 degree change of Celsius. You can see that the units will work out so that the kilograms cancel, the Celsius or the Kelvin will cancel, and heat is a unit of energy. It is a transformation between types of energy, right? Work and energy are the two types of transitions, and the amount of heat you add or take away would be in joules. It is still a unit of energy. Okay, so there's some typical numbers for you. And this will be on the worksheet today. You don't have to memorize this at any time. They'll always be available to you on exams, quizzes, whatever. You don't have to memorize them. You just have to know that these things exist. Those of you who've seen the CRC chemical handbooks, there's pages and pages of tables of specific heats of solids that you can look up. Heats of transformation. Now we're talking about a phase change. And again, from last time, the heat that is required to cause a phase change is the mass times this thing called the heat of fusion or the heat of vaporization, L sub F or L sub V. I think the word L comes from the word latent heat of fusion. Sometimes people use that word, or latent heat of vaporization. Okay, and you could see fusion is when you melt or freeze, and vaporization is when you either boil or condense. Okay, and it's plus or minus heat depending on which direction you're going. You have to add energy in order to melt and to boil. So it'd be positive in that case. And here's some typical numbers. And I guess the one we care about the most is water. But I think it is interesting to notice that in general, taking something to the gaseous state, the latent heat of vaporization, those numbers for any material are typically bigger than taking something from a solid to a liquid state. So from liquid to vapor takes more energy, apparently. All right, that's all I got. Any questions on any of that? Most of that's review, I think, other than maybe that graph that was in today's lesson. We did most of this on Friday. So here's the first question. And oh, look at that, spelled question wrong. Yeah. All right. Let me get a tool to draw. "19 people in. We've been going about a minute here. All right, I got 20 to 23 people in. We've been going about a minute and a half. I'm going to end it. I'm going to share the results. And I'm going to say, it's early on a Friday. I'm disappointed, but what the heck. So here's the equation we just said, right? Q is equal to the mass times the specific heat times the change in temperature. And key word here was certain amount of heat, 1 gram of material A and also 1 gram of material B. That means Q here is the same for both materials, and the mass is the same for both materials. And so really we're just trying to figure out what the relationship between the specific heat and the temperature changes. So I'd solve for specific heat, right? Q divided by the mass divided by delta T. And Q is the same, remember, and M is the same. And so you can see that the specific heat and the temperature change are inversely related. So a greater temperature change results in a lower specific heat. And so material B, which changes by 4, would have a lower specific heat. Material A, which changes by 3, has a higher specific heat. And so unfortunately here, the 6 of you, not unfortunately, good for the 6 of you, the 6 of you who pick material A, I think you've got the right idea. You know, if you think about mass as a measure of inertia, and this is a rough analogy, believe me, but right, if you've got a bigger amount of mass for a particular force, you get a lesser acceleration. Specific heat's sort of like that, isn't it? It's almost like a temperature inertia. You put some amount of heat in, which is not exactly a force, but work is a force times a displacement. So it has that motive kind of thing. It's going to change something. It's going to change. Heat is going to change the temperature, just like force is going to change the acceleration, or change, which ultimately changes the velocity. So C there has that. It's almost like temperature inertia. The bigger C is, the harder it is to change the temperature. Just like the bigger the mass is, the harder it is to accelerate something. And I think that's a legitimate way of viewing it. Although the analogy is rough, the fact is mass and acceleration are multiplied together, just like specific heat and temperature are multiplied together. And so they must be inversely related. All right. Any questions on that? All right, we'll see if it gets a little better here. Let's go on to the next one and launch this poll. And I gave you the table, as I said, just like specific heats, latent heats of fusion and vaporization, and respective melting and boiling temperatures, you'd never be expected to memorize, although I suspect most people know water melts at 0, freezes at 0, boils or condenses at 100 C. So again, equal mass, which is going to happen first? The ice will melt or the water will boil to steam? And of course, here I'm checking to make sure you know what watts are. What is power? All right, we're about a minute and a half here. Number of people we got 16 out of 23 people have made a decision here. 17, there you go. Make a choice. All right, well, we're cutting it off. And I'll share the results. And the majority wins here, but for the 70 that went, boiling will happen first. Take a look at the numbers right here. 22 times 10 to the fifth as opposed to 3.3 times 10 to the fifth. That means for the same mass, greater heat must be added to boil. Okay, so that's the first step. So less heat to melt, just because of the ratio of the numbers right there. All right, and then of course, that is a constant rate. Remember, a watt is a joule per second. And so if you're looking at the time it takes to either melt or boil all the water into steam, greater energy required at the same rate, well, it'll take longer to boil the steam. So the ice will all melt first. And I think that's the answer to the question. So there's 10 people who picked that. That would be the answer. All right, next one. And this one is, you kind of got to do a little math in your head, I think. Not much. You don't have to pull out a calculator because all you got to do is decide relative to halfway between boiling and freezing, what's going to happen here. So you've got a kilogram of silver at 100 degrees C, dropped into a kilogram of water at 0 degrees C, and you're given the specific heats. Where's the final temperature going to be? And by the way, this is a calorimetry experiment. It's exactly what we're going to be talking about and calculating today. All right, we got 17 people in. That's exactly the number played in the last question. So I'm going to assume everybody else is either bored or has internet. Look, we got 2 more. 19. I'll end it there. Take what I can get. All right. And the majority are going between 0 and 50 degrees. And I agree with that. And so let's talk about a calorimetry experiment, which is what this is. And I'll show you the equations that you have to work up, and I'll unpack the equations, which I think is an important part. Okay, so what do you expect is going to happen to the silver at 100 degrees C? Well, I think it's going to cool down. And what's going to happen to the water, which is right at apparently it's just melted at 0 degrees C, okay? And the answer is it's going to heat up. And so, although we've talked about the heat that is needed to either melt or raise a temperature or boil, we've never really discussed where it comes from. And this problem is answering that. So if this system is isolated, the heat that raises the temperature of the water comes from the silver. On the other hand, the heat which is removed from the silver, well, that goes into the water. And so if the thing is isolated, we think that energy is conserved. There's no heat going out boundaries. And that's always a iffy assumption, but it's the one we make, much like frictionless surfaces. We have perfectly insulated barriers. Okay, so 0 has to be equal to the heat, I guess, added to the water by the silver, Ag silver, right? Been a while since I took chemistry, plus the heat that is being put into the water has to be equal. Okay, and I think this number is actually a negative number. There is heat being lost by the silver, and the water is actually gaining. And let's see if that makes sense. Okay, if these are positive and negative, and we'll see why here, hopefully, as I write this out, that's the mass of the silver times the specific heat of the silver, which you can see is significantly less than water, right? Significantly less, times the temperature change, and that means T final minus T initial, plus the mass of the water times the specific heat of the water times the final temperature of the water minus the initial temperature of the water. It's supposed to be an I there, but I guess I can actually run onto that little side piece there. That's why I keep it. Okay. And now why is this heat from the silver negative? Well, the initial temperature here for the silver was 100. You expect it to cool down. So this is going to be a number less than 100. This thing in parentheses is how the heat from the silver becomes negative. On the other hand, the water started at 0 degrees. That's supposed to be initial right here. Its initial temperature was 0, and it's going to heat up. So this term in parentheses is going to be positive. And that's why I say the two add up to be 0. And here's, I guess, the point. Because the silver specific heat is so much less than the specific heat of water, I expect that I am going to need a much greater change in temperature here than I'm going to need here in order for these two to be equal but opposite in sign such that they add to 0. Because this is small, this thing I circled must be big in order to be equal to this thing, which is big. So I really don't need much of a, let's see, I guess yeah, it's a drop, but I don't need this thing to be as big. And so I don't need the final temperature to be very large. Now, that hopefully makes sense to you as an algebraic equation. You just add these things up and you be careful about initial and final, remembering that the change in anything from the first week of class is the final minus initial. And the signs should just work themselves out. In the worksheet problem, which we're going to go to next, there's going to be 3 things. Okay, and you're going to have to calculate what the final value is. All right, so I'm going to stop sharing this. Any questions on this? The new wrinkles today in calorimetry are we've only addressed, well, what change in temperature results from heat being added, what change in phase results from heat being added. We haven't really talked much about, well, where does that heat come from? Today's topic addresses that a little bit. It has to come from some other object. In this case, the silver and the water interact together. I'll stop sharing this. And I want to go over to my iPad, which has today's worksheet on it. And hopefully it'll do its thing. Screen mirror. All right, and hopefully you're seeing today's worksheet, which is 12.1 on calorimetry. And same table of specific heats that we showed just a moment ago in the PowerPoint. The one that I did have to add to do this problem is glass, because we needed a container. And so I added glass. I looked it up in another textbook. 840 joules per kilogram Kelvin is the specific heat of glass. And so here's the experiment we're doing. And I still haven't ruled this experiment out as our lab for next week. I expect if I don't do it next week, then Dr. Kaiser will work it first week of PHY102 for those of you coming back, and I hope most of you do. We actually have the apparatus to do this in Dunning Hall. We don't use glass, we actually use styrofoam. It just insulates better, but there's my container. You have to know the mass of the container, right? It's a glass beaker, 225 grams is the mass of the glass in the beaker. And then there's some water, okay, in the beaker. And how much? 220 grams of water. And then you take a piece of copper, that's referred to as a slug, just somebody melted and made into maybe a cylinder or just a cube or something of copper. And we actually lower it in with a string so you don't burn your fingers, because somebody heated it up to 312 degrees, maybe with a Bunsen burner and some sort of contact thermometer that allows you to, non-contact thermometer allows you to maybe figure out what the temperature is without again putting the thermometer in contact with the copper, which of course would cool it down. So we're trying, we know that information, and then we lower the copper into the water, and then we watch and we let everything come to equilibrium. And the question is, what will the final temperature be in this case? As an alternative, you can measure what the final temperature is and back calculate what the specific heat of copper is. Of course, in this case, we know it. 385, you're going to need that number, and you're going to need where is it? Water, right there. You're going to need those numbers. And so I'm going to do the first one. Then I'll leave you to do parts 2, 3, and 4 to figure out what that final temperature should be. And the problem when I say write an equation, that means think about in the equation what numbers you know and what numbers you don't know. And so heat lost by the copper, okay, that's Q, we'll call it copper, right? Cu. And you better subscript things, otherwise you'll be getting yourself confused, is equal to, of course, the mass of the copper times the specific heat of the copper, C sub copper, and then the change in temperature of the copper, which is the final temperature minus the initial temperature, okay? And that's, of course, of the copper. And I wrote that without a subscript, okay? So it was just T. And now I can fill in, what do I know here, okay? I guess I know the mass of the copper, convert it correctly to kilograms, okay? The specific heat of copper looks like 385 joules per kilogram Celsius. And remember, the fact that that's Kelvin is okay. If I'm in Celsius, 1 degree change of Kelvin is 1 degree change in Celsius. And then, of course, my initial temperature, 312 Celsius. So the only thing I think I don't know in this, at least on the right side, is what's the final temperature? Okay, you can go through exactly that same process for the water and the glass. Okay, and remember, in this case, I tell you that the water and the glass are initially equilibrium with each other at 12 degrees C. And so you can go through exactly that same thing, write those equations, and then I'll give you the conservation of energy equation here. It's exactly what we talked about. If the glass is thermally insulated, put a real good koozie on the outside of the beaker, for example, then no heat's lost, no energy is lost. And so the energy in the copper, the heat of the copper, and I expect that to be a negative number. I expect that to be a loss, right? It's going to cool down. So its final temperature is going to be less than its initial temperature, plus the heat of the water, plus the heat of the glass. I don't know what the symbol for glass is. I'm just going to write out glass. Those all have to add up to be 0. Again, assuming that no energy is lost across the boundary. And I think this should turn out to be a negative number. These two guys are going to heat up, the glass and the copper. So I expect those are going to be positive numbers because their final temperature is going to be greater than the 12 degrees. And of course, the problem is the algebra of extracting the final temperature, which is in each of those heats to figure out what the final temperature is. All right. And so I'm going to break up into groups here in a second and leave you all to work that. And I'll jump around and ask questions. I'll tell you that the final answer is in the vicinity of room temperature. It's going to go from 12, which is pretty cold water, up to the vicinity. It'll heat up to somewhere in the vicinity of room temperature. So you'll know if you're in the right ballpark if you get a number near to that. All right. This one I think is a little straightforward. More straightforward. Okay, so now we've got a full kilogram, 1,000 grams of tap water. It's at 20 degrees C. And I want to know how much energy you have to put in order to raise the temperature up to 100 degrees C. Okay, and then boil all the water away. And so hopefully you realize you're going to need numbers from the chart on the front page. Okay, the specific heat of water. And then you're also going to need the latent heat of vaporization in order to do that calculation. All we need to know is how much total energy in joules it takes to bring water from 0 degrees, it just melted apparently, up to 100 degrees, and then to make all of it boil away, all of that at equilibrium. So we don't have to worry about it. Any questions on what we're doing? All right, those are the two problems. If you don't finish them today, you've got about 20 minutes to work on them. They're due Monday morning. But go ahead, if anybody wants to come back and show their solution in the last, 2 minutes of class, well, then you don't have to upload it, I guess, so you save yourself a step. I'm going to stop sharing that. Looks like we got 25 people here. Let's see, 5 groups of 5. Yeah, why don't we go 5 groups of 5 then? Breakout rooms, groups of 5, and we'll see you in a little bit. I'll be popping around, answering any questions you got.
So Dr. Tulski, I just want to make sure that I'm on the right track.
Okay.
Um, do you just follow the same pattern that you did for question one? Just take all the information from the question and the table, and then add all of those equations up to equal zero.
That's it. Yeah.
But you don't
And
have to. You don't have to find the individual energies for
no,
each.
in
Just
fact, you can't because until you know the final temperature, it's just a
okay,
symbolic equation, right?
got it.
Yeah. And so the fourth question is actually the hardest because that's where you have to manipulate all the unknown final temperatures, which is in each of those three Qs,
Hmm.
and solve for that final temperature. So
Got
the
it.
algebra is kind of a pain in the butt on the last one, right? Because you got temperature final in each of those Qs. You got to separate it out, get it to one side of the equation, do the division, and solve for it. If you got one of those neat calculators that'll you just type the whole equation in and say solve for this, it goes a whole lot quicker. But if you got to do it algebraically, it took me about 4 lines to do, and it was lots of symbols being written out. All right. So yeah,
Yeah,
4 is the hardest part, even though it looks pretty easy because that's where you do the algebra, finally do the algebra.
got
There
it.
you go.
Yeah, yep.
All right. Have fun with it.
Wait,
And
hold
then
on. How do we find the final temperature?
Dr. Tukolsky,
Yeah.
we're not
That's the question right there. Algebra is the answer, but we'll talk about that in a second. Go ahead, Nita.
okay, we're not solving right now for this number 3. We're just writing the equation.
Yeah, you're just writing the equation. You can't actually solve for it until you have all 3 equations written out.
That's what I was saying. So we got the other equation. I just haven't written it. It's
Okay.
the QW equals.
Actually, that's gonna be QG, right? Yeah, G.
And are they both positive because they gain? And
Because the final temperature is going to be greater than 12 degrees. Yes. So T final minus T initial is going to be a positive number.
okay, so both the Q's are positive.
Both of these two are. But remember, the one I wrote out
It's negative.
is negative. And now, if you think about it, you have all the numbers in these two equations except for that final temperature. Same thing in the one I wrote out. The heat lost by the copper is equal to the mass of the copper times the specific heat of the copper times T final minus the initial temperature of the copper. Again, all 3 of those you don't know final temperature. So what do you think you have to do in the fourth part? A lot of algebra is
Set
the
them all
answer.
equal to 0.
Yeah, you set them all equal to 0 and you try to solve for that final temperature, and it's going to be in each of those Qs. So you've got to distribute out the mass and the specific heat on each of the temperatures, get the unknown final temperatures all together, get them to one side of the equation, factor out the final temperature, and then divide through by the things you factored out in order to find that final temperature.
When you say set them all up to 0, are we like each equation individually equal to 0?
No, the sum of the 3 is equal to 0.
So
No.
Yeah, and that it just makes it a hard algebra problem, truthfully, in number 4, but you can do it. Here's an
So would it
example. Here's an example of
positive?
what you might have to do, and I'm going to write right over here. So let's say I had an algebra problem where, and much easier algebra problem. I need a pen here. There it is. Let's say I had that 6 times x minus 2 is equal to, let's go this way, plus 12 times x minus 7 is equal to 0. That's essentially what you have, right? Because these are just 2 numbers you know, and this one you don't know. So that's like the x. But this you do know. That's because that's 12 Celsius, right? So you know the coefficient out front, you know this. Okay. Well, you can solve for this, right? You have to go 6x minus 12 plus 12x minus, I should have picked easier numbers, 84, I guess, minus, let's see, yeah, minus 84. I think that's what 12 times 7 is.
I have a
okay,
question.
is equal to 0. And now you can move these to the same side of the equation, move these to the other side of the equation, and you can solve for what x is, right?
I have a question.
That's essentially what you're doing, except you got 3 terms, not just 2. Go ahead.
So instead, let's start with water. We have our equation. Instead of the Q or copper, instead of the Q of the copper, put that as 0.
No, I think I've only, let's make it almost exactly what you have to do.
Solving
Okay.
for
You have a
final
third term. The one I wrote out was, oh, come on, go back to a pen. So you might have another one, 17x minus, oh, I don't know, 300. All that's equal to 0, right? Actually, this was 312, this was 12 degrees, this was 12 degrees. These numbers out front are all going to be the product of mass and the specific heat, and you have to solve for x. Okay, and yeah, so you've got 2 of the 3 equations. The third one was Q copper is equal to the mass of the copper times the specific heat of the copper times the temperature final. And I'll just write the number minus 312 because that was the initial temperature of the copper, right? As opposed to 12, which is right here. And so from the table, you know that number, you know that number, you know that number, you know those products. The only thing you don't know here, final temperature there, final temperature there. That's supposed to be an F. Now that I look at it, it's a lousy looking F right there. That's your unknown right there. And you know, but you do know that QC, heat of copper plus heat of the water plus heat of the glass has to add up to be equal to 0. So you're going to put all this stuff right there, this stuff right there.
Wait, wouldn't it be minus heat of
Well,
copper?
I think it becomes minus because the final temperature is going to be less than 312 degrees. So this thing's going to naturally turn out to be negative. But right now, I think you just leave it the way it is. Okay. Yeah, the math will work it out for it. Whereas in both the water and the glass, the final temperature is going to be greater than 12. And so that's going to make those two become positive when you do the algebra.
That is
Right?
like,
See what you got to do? Yeah, I know it's a pain in the butt algebra, but you can do it. And if you got one of those cool calculators, or you go to one of those websites like MathNet, you can just say solve, give it everything, one unknown, it'll solve it for you.
but isn't QCU unknown, which I don't understand how to find if we have 2 unknowns in the equation?
Well, I think you substitute for QCU this equation right here that only has the one unknown, the final temperature. Heat of the water is also unknown because you don't know that final temperature. So you substitute this. In some ways, I guess it's 4 equations with 2 unknowns, right? So you can solve that. You completely eliminate the fact that.
Am I able to show you that?
Say that again.
Oh no, I'm so sorry. No, it's not.
Okay. Yeah, so you got to do some algebra. It took me about 4 or 5 lines to do, but I think you can do it. All right. Work it out. See you in a bit. I know. Where do I have to go? I want to go to another breakout room.
All the final temperatures would be the same, right?
Yes, that's the key point. They're all the same. That's your unknown variable. Let me call it X if you want. All right, the other groups were all lamenting the algebra that you have to do when you get down to step 4. Y'all okay with that algebra?
Yeah, so how do we know that the copper is negative again?
Yeah, the reason you know copper is negative, hang on, let me share. It'll just turn out that way for you. That's the good news. You don't have to worry about that fact. All right, where to put my whiteboard? Come on. Oh, there it is. It's just underneath these toolbars here, which I can put away. All right, so what we said was that the heat of the copper is equal to the mass of the copper times the specific heat of the copper. Those are both things you know. You can multiply them out and get a number for that. Temperature final, and then minus temperature initial, which I think was 312. The reason this is going to turn out to be negative is because this is going to turn out to be a number, I don't know, maybe it's 30 degrees, right? So 30 minus 312 is going to be a negative number. All right, but look at the water, H2O. Same equation, only mass of the H2O, specific heat of the H2O, same temperature final, because eventually it comes to equilibrium, but this is going to be minus, what's the initial temperature, 12 degrees C, right? And again, you know these numbers, you can just multiply them together. That's just a coefficient basically out in front. That's just a coefficient out in front. And then the same thing for the glass, right? The heat of the glass is going to be equal to the mass of the glass times the specific heat of the glass, same temperature final. In this case, it started at 12 degrees also. You know those things, you can just multiply them out. The only unknown here is that final temperature. Now, the reason this one's negative is because the final temperature is going to be less than 312. These two are positive because I expect the final temperature is greater than 12. I expect these two things, the water and the glass, are going to heat up. And so my expectation is that the final temperature will be greater than 12. And so this becomes a positive number and this becomes a positive number. But you don't have to worry about that right now. What you have to worry about is putting these all together, okay? So that the heat of the copper plus the heat of the water plus the heat of the glass, that's a Q, of the glass, all add up to be equal to 0. And the only way that can be is if at least one of them is negative, right? And it's going to turn out to be the copper is the negative one. That one's going to be positive and that one's going to be positive just from what we expect from the physics. Our intuition says if I put that hot copper into the water, it's going to heat up the water and the copper is going to cool down. And so that's what I expect is going to happen. But at the end of the day, this is a lot like an algebra problem, right? Oh, I don't know, 17x minus 5 plus 23x minus 5 plus 72, and I'm just making up numbers here, x minus 500 is all equal to 0. And of course, you got to get the right numbers here and here and here and here. And it's a pain of an algebra problem to do, but you could solve that thing for x. In this case, x is your final temperature. See what you're doing?
Yeah, thank you.
Yeah, probably more than you needed. I probably could have stopped about 2 or 3 minutes ago. All right, that's the problem. And 4, it took me 5, 6 lines of algebra. 1, 2, 3, 4, 5 lines of algebra to do it. Maybe it takes you a little more. If you got one of those super TI inspired calculators that you just put an equation in and say solve for the unknown, even though the unknown's in 3 different places, it'll do it for you. The rest of us have to work out the algebra by hand. Okay?
Okay, thank you.
You bet.
I got 19.6 for the first one.
I like it. That's it. So y'all figured out how to do the algebra, how to set it up, and I agree with 19.6. Did you work it out or did you have one of those cool calculators that you just put the equation in and say solve?
I have a calculator.
Yeah, isn't that nice? You don't have to manipulate the equations to get that. Yeah, all right, good. 19.6 is the same answer I got. The second problem is pretty straightforward. Should take you just a second or two. All right, I'm going to leave because you guys got it. I'm going to leave if I can find my toolbar, that is. There. All right, any questions? The other three of the other groups were lamenting the algebra, which I admit, part 4 is an algebra problem. If you got one of those cool calculators, it doesn't take that long. Otherwise, you just got to do a lot of manipulation. Do you know how to set it up though?
I'm good personally.
Good to go. Okay, did you get a number yet?
I got 19.6.
Perfect. Yeah, you're good to go. Yeah, and do you have one of those cool calculators that'll you just put the equation in and say solve for the unknown, even though it's in 3 places? Or did you?
No, I kind of manipulated it a little bit.
All right. Well,
It wasn't bad.
we respect you for doing that. Well, I agree with you. Some people don't like to do that kind of work. It is
Yeah, because it can get messy because when you have to like distribute and stuff
Exactly.
like that, that's when it gets all messy and you just got to make sure you keep your work in line.
Right. And if you write down the wrong number at any place in distributing, the whole problem will turn out to be wrong. But I agree, 19.6, so you kept your facts right. All right. I think we're done here. It's right around 9:20, so I better end the rooms. All right, looks like most people are back and our time is up here this morning, so I got to let you go. I do want to tell you the 2 groups had the right number, at least 1 or 2 people in it had the right number. And the number declared was 19.6 Celsius, almost room temperature, I guess, right around room temperature. And I agree with that number. So that's what you're shooting for. I do admit that when you get down to step 4, it's an algebra problem. I think Michael confessed he's got one of those neat calculators that even though the unknown is in 3 different terms, if you type the equation in and tell it to solve, it'll go do it. Those of you that don't have a neat calculator like that, I showed you last week, Wolfram Alpha. There's also Symbol Lab is out there to do symbolic calculation like that for you, where you type in the equation, tell it to solve for the unknown. MathNet is another site. So if you don't have the great calculator and you're worried about working it out, it's very easy just to write the wrong number while you're distributing constants over an unknown and another constant. It's very easy to make a little mistake in there. And then of course, one little mistake and your final answer will be wrong. So you can use those kind of calculation tools. They'll be available to you on the final exam. If you don't have one of those neat calculators, but you want you can do it on the website and still check your work and make sure you're getting the right number. And that's all I got. Any questions? Yeah, somebody's about to ask.
Okay, so we solved my group, but all 3 of us got different answers. So can I ask you, what did you get?
I got 19.6.
That's what I got. Okay, so
Okay,
guys,
and that's what Michael got, and I forget who was talking to me. The person who worked it out by hand, which I have great respect for, by the way, because that takes a very high degree of attention to detail.
Yeah, I did it by
working
hand.
it out. Yep, 19.6 looks like the right answer.
Thank you.
All right. Any other questions? All right, I'll stay around. I won't have the office hours at 10:30, but I'll stay around until all questions are answered here. If you got to go off to class, have a great night, a great day, and a great weekend. Hopefully the weather will improve for us.
Thank you.
Take care now.
Can I see